Okay, you know that super frustrating glitch in video games, right? Where something just, poof, clips right through the water like it isn't even there? Well, that bug might just be history. Today, we're going to break down the absolutely incredible technique that finally solved it. And get this, we'll also uncover some really surprising life advice that's actually hidden inside the research paper. And then, we're going to put the whole thing through the ultimate reality test.
So you gotta ask, why? Why do these super complex simulations get something so basic so completely wrong? Well, it's not just some simple coding error. No, simulating how objects and fluids actually interact, that is a genuinely hard problem in computer physics. I mean, we're talking about something that has stumped some of the brightest minds out there for years. And let's get one thing straight right off the bat. There's no AI here. No fancy neural networks just guessing what should happen. Nope. The solution we're about to dive into is pure physics. It's all about human brilliance and having a really deep understanding of how nature actually works.
Okay, so this right here, this is the heart of the whole problem. Think about it. Water is super heavy, right? Super dense. But air is about 800 times lighter. For a computer, that is a total nightmare. I love this analogy. It's like trying to simulate a sumo wrestler dancing with a tiny little mouse without, accidentally crushing it. The math just becomes so unstable that the whole simulation often just blows up.
And this is where our breakthrough comes in. It basically takes the old, chaotic way of doing things and transforms it into something completely different. We're going from like a violent mosh pit to an elegant synchronized ballet.
Yeah, seriously, just picture a chaotic mosh pit. That's how most simulations used to work. You've got solids and fluids just crashing into each other, there are no rules, everyone's stepping on everyone else's toes, and the result is just totally unpredictable and frankly unrealistic. It's pure chaos.
But this new technique, wow, it changes everything. It literally turns that mosh pit into a perfectly synchronized ballet. It provides a set of rules, almost like an etiquette guide, and the result is, well, it's some of the most realistic physics simulations anyone has ever seen.
And the results, just look at this stuff. They're absolutely stunning. We're seeing air-driven turbulence from a propeller that isn't even touching the water. We've got raining cows and bunnies of different densities creating these incredibly complex bubbles and swirls. There's even an airplane ditching where the splash is so powerful it literally hits the ceiling. And look at this one. It perfectly shows how a realistic air bubble forms in front of a car underwater. The level of detail here, it's incredible. Okay, so how is this even possible? Right? How does this technique get these beautiful, stable results? Well, let's pull back the curtain and unpack the secret behind this incredible dance.
The secret has a name. It's called the Lattice Boltzmann Method. Now, to get what that means, imagine the old way as like a manager shouting vague instructions at a whole crowd through a megaphone. This new method is way more precise. It's not tracking every single molecule. Instead, it's calculating the probability of finding little groups of particles moving in certain directions. So it's less like shouting at a crowd and more like whispering specific instructions into the ear of every single particle, every single dancer on the floor.
And here's how it works. It breaks things down into two totally separate steps for every single particle. Okay, step one, there's a dedicated block of time where particles just get to move freely. They just flow forward, all by themselves. Then, in a completely separate time slot, step two happens. They get to collide and interact with each other. By separating the flowing from the colliding, you see what's happening? The simulation avoids all those cascading errors that made the old method so unstable. That separation, that is the absolute key. And this is where we get some genuinely profound life advice, straight out of a physics paper, of all places. Ready for this? You cannot flow and collide at the same time. Just think about that for a second. Think about your workday, right? It's filled with constant meetings, collisions, leaving you with these tiny little blocks of time to actually get work done, to flow. It's impossible to get into a real flow state. Just like these particles, we need dedicated time just to move forward without all the interruptions. Okay, so the other huge piece of the puzzle here is something called two-way coupling. This is the real magic that allows for true interaction. All it means is that the water pushes on the object, and, this is the crucial part, the object also pushes back on the water. It's a constant two-way street of communication.
So how does it actually manage this constant conversation? Well, remember our ballet? The method basically provides an etiquette guide for all the dancers. It tells every single particle exactly what to do when it bumps into something else. How to bounce back, how much energy to transfer, and how to exchange momentum properly.
And believe it or not, this brings us to our second piece of incredible life advice from this paper. Think about it. Successful relationships, just like a successful simulation, require two-way coupling. Both people need to influence each other. You can't just push your way through every decision. That power, it needs to be shared, or eventually it's lost. Wow.
So, okay, the theory is beautiful, right? But does it actually hold up in practice? Let's find out. Let's see how this new method performs when it has to face the ultimate judge, reality itself.
Now, you'd think all this extra realism would come at a huge performance cost, right? It's got to be slower. But just look at this. The new method isn't just better, it is a staggering 4 times faster than the old way. I mean, that's incredible. And that kind of efficiency doesn't just mean better video games, it opens the door for all sorts of complex industrial simulations. We're talking designing more efficient jet engines, or even modeling how blood flows through our arteries. This is a huge deal. And that performance unlocks brand new possibilities. Take stone skipping, for example. Most older simulations are just too sticky to get this right. The stone just plunks into the water. But this method is so precise, it can actually simulate that tiny, thin layer of air that gets trapped between the stone and the water. It gives the stone its own little personal space on the dance floor. And that's what lets it bounce just like in real life.
All right, and now for the ultimate test, the toughest one yet, a direct side-by-side comparison. On one side, we've got our simulation. On the other, a real-life video of a key dropping into water, filmed with a high-speed camera. Let's see how it stacks up.
And you can really see this play out in 3 acts. Okay, Act 1, the breach. The key just slices the surface so cleanly, no clipping at all. Then Act 2, the veil. Look at that beautiful pocket of air trailing the key. It looks just like a bridal veil. It's an exact match to the real thing. And finally, Act 3, the collapse. The water pressure crushes that veil and it just collapses into this turbulent cloud of tiny bubbles. It is a perfect match.
So, what's the big takeaway from all this? I mean, this isn't just about a better way to simulate water in a video game. It's about a much deeper appreciation for how physics, life, and just the incredible beauty of the natural world all intersect.
You know, the person who first brought this research to light pointed out that pretty much nobody was talking about this brilliant work. And when you think about it, that really is a tragedy. It's exactly why it's so important for us to amplify these kinds of incredible under-the-radar scientific achievements.
And hopefully, this inspires all of us to just look a little closer at the world around us. I mean, the next time you're by a stream, just stop and watch how the water flows around the rocks. What you are literally seeing is the original two-way coupling, a calculation that Mother Nature computes perfectly, millions of times every single moment.
It's a really humbling reminder, isn't it? We work so incredibly hard to try and simulate these systems, but nature's own code? It's already perfect. It runs flawlessly at the speed of light all around us all the time. Which kind of leaves us with one final thought to ponder. If this level of elegant, complex physics is happening in something as simple as a stream, where else is nature's perfect code hiding? Right there in plain sight, just waiting for us to notice.